This is a walkthrough of problem 4 on exam 1 of module 7 in the book Problem Solving Guide for Electromagnetism and Optics. Problem 4, we have a slab of aluminum, 5 centimeters in this direction, 1 centimeter thick, carries a current, conventional current I, to the left as shown in the figure. The ions have a drift speed of 2 times 10 to the minus 4th centimeters per second. There's a magnetic field perpendicular to the broad face of the bus bar, either into or out of the page, that has a magnitude of 500 millitesla. The magnetic field produces a voltage difference between the top and the bottom of the bus bar. That's called the Hall voltage. The polarity is the positive on top, negative on the bottom. We can put that in. Part A reminds us first that the direction of the conventional current is wrong. The electrons are moving to the right, the opposite direction of the conventional current. And it's asked, what is the direction of the magnetic field B? You have to choose from into or out of the page. So the conventional current's to the left, the electrons are moving to the right. And we know the magnetic force is downwards because it's pushing these electrons downward. That's why they're there. If the magnetic force on a negative particle is downward, the direction of V cross B is upward. So we have the direction of V cross B upward. We stick our thumb to the right, the direction of the velocity, and our palm is up. Our fingers point in the direction of the magnetic field, which is into the page. So B is into the page. Well, part A, the answer is the magnetic field B is into the page. Now let's do part B. What is the magnitude and direction of the magnetic force on an electron moving at the drift speed? Magnetic force is Q V cross B. The angle between the drift velocity and the magnetic field is 90 degrees. So the magnitude of FB is just QVB. And I think we have everything. There's the electronic charge. There's the drift speed after converting from centimeters per second to meters per second. And there's the magnetic field converting to Tesla. And we get 1.6 times 10 to the minus 25th newtons downward. The magnetic field is pushing the electrons downward. Part C asks, what's the magnitude and direction of the vertical electric field? There's positive charge on top, negative charge on the bottom. That's producing a vertical electric field. And of course, it's going to push negative electrons upward. The magnetic force is downward. The electric force is upward. They balance. The electrons will go straight through. The vertical electric and magnetic force is balanced. The electric force must be the opposite of the magnetic force, which is 1.6 times 10 to the minus 25th newtons upward. Part D, the vertical electric force is this. The vertical field, remember this distance is 5 centimeters. F is QE. There's the force. There's the charge. 1 times 10 to the minus 6 volts every meter. Delta V is E times D multiplied by 5 centimeters after converting to meters. And we get 5 times 10 to the minus 8 volts, which is 50 nanovolts. That's problem 4.